Hello everybody, get ready to do lesson 10.3 part 2 of pre-calculus math today. And for today's lesson we got 8 points that will go into your notebook sheet or guide, have that out. And then we have 26 points will go into your notebook guide, have that out. Name, date, period, due date for onliners and holders. We're going to go right into it today, students, right to your notebook. In example 2, going back to the previous part 1, note that you could have used the cross product v times u to form a unit vector that is orthogonal to both u and v. With that choice, you would have obtained the negative of the unit vector found in the example. So the fourth geometric property of the cross product states that the directed vector u times v is the area of the parallelogram that has u and v as adjacent sides. So this will find the area of a parallelogram that has u and v as adjacent sides. A simple example of this is given by the unit square with adjacent sides of I and j. Because I times j will equal k, and the directed vector of k equals 1, it follows that the square has an area of 1. So that is almost like a test of this finding the area of a parallelogram. This geometric property of the cross product is illustrated further in the example. So going from that, geometric application of the cross product show that the quadrilateral with vertices at the following points is a parallelogram. Then find the area of the parallelogram. Is the parallelogram a rectangle? Is the final question. So here are vertices here. So from the figure, then here is our illustration of this quadrilateral with these vertices here: 506, 247, 520, and then 261. So the sides from the figure, you can see that the sides of the quadrilateral correspond to the following 4 vectors. So now we have 4 vectors now. Vector AB equals the negative 3i plus 4j plus k. And then CD, the vector CD here, which would be CD, is 3i minus 4j minus k, is the negative of AB. Guess what? It's the negative of this. So AB here, we got AB, and then CD is the negative of that. CD is the negative of vector AB. And then here we have AD. AD is 0i minus 2j plus 6k, and then CB is the negative of that. So we have 2j minus 6k equals the negative of AD. Isn't that interesting? So AD, which is here, and then CD is the negative of that. Okay, so what are we going to do with that? Because vector CD equals the negative AB and vector CB equals the negative of vector AD, you can conclude that vector AB is parallel to vector CD and vector AD is parallel to vector CB. It follows that the quadrilateral is a parallelogram with vector AB and vector AD as adjacent sides. So here's the key word here: adjacent sides. Moreover, because vector AB times vector AD, and then here is our array here, ijk, it comes out, when you multiply this out, it comes out to 26i plus 18j plus 6k, and then the area of the parallelogram is the directed multiplication here of vector AB times vector AD equals this. So we put this underneath a radical. We have radical 1036, which comes out to 32.19. You can tell whether the parallelogram is a rectangle by finding the angle between the vectors AB and AD. So we take sine theta of the directed vector of AB times AD over vector AB times AD, each one of these independently versus the this product here. And when we do that calculation, we end up with sine theta equals radical 1036 over 26 times 40. And then this comes out to sine 0.998. So when you take the arc sine of that, we come out to with 86.4 degrees. So because it's not a 90 degree here, the parallelogram is not a rectangle. If it was a 90, it would be classified as a rectangle. Isn't that cool? So let's try one here. And these exercises, A, we have A here, we have B here. A is verify that the points are the vertices of a parallelogram. And then B, find its area. And C, there is a C part, determine whether the parallelogram is a rectangle. So this is guided practice. So for A, we have AB here equals this, is parallel to DC. So do we know that? It is. We have 1, 2, negative 2 is parallel to DC. Verify that the points are vertices of a parallelogram. Okay, so I guess we're going to say that they are. Now, this is your answer sheet, students. If you want to, you could plot these. I mean, that would be another visual way of doing it. Be to plot these. Is parallel to this, and then AD is negative 344 is parallel to BC. So we have AB. Is that we're going to assume that they are is parallel to DC, and then AD is parallel to BC. So AD would be parallel to BC. So that's what we come up with there. That's A. Verify the points that are vertices of a parallelogram. And then B here, find its area, and so we're going to find the area here, and we set up this array here, vector AB times vector AD, and then here is our, what we come out with here is our component vector, 16, 2, and 10, and then the directed AB times AD equals 16 squared plus 2 squared plus 10 squared. And then this comes out to 360, and then 6 times radical 10 square units would be the area of this parallelogram. And then for C, to finish, this is all guided practice. C would be vector AB times, well, this would be line segment AB times line segment AD. When you multiply this together, it does not equal 0, so it's not a 90-degree angle, so it's not a rectangle. The triple scalar product for the vectors u, v, and w in space, the dot product of u and v times w is called the triple scalar product of u, v, and w. The triple scalar product. So for u, we come up with this here, this whole array here of different factors with each other, u1i plus u2j plus u3k, then v equals v1i plus v2j plus v3k, and then w equals w1i plus w2j plus w3k. The triple scalar product is given by, here it is, u times the quantity v times w, and then this is what your matrix will look like for this, the triple scalar product. When the vectors u, v, and w do not lie in the same plane, the triple scalar product u times quantity v times w can be used to determine the volume of the parallelepiped or a parallelepiped. That is a polyhedron all of whose faces are parallelograms with u, v, and w as adjacent edges as shown. So that's what it is. All of whose faces are parallelograms. And this is the fancy word for that, a parallelepiped. This is what it looks like. So the area of the base will equal the vector v times w, v times w. The volume of the whole thing will be u times the quantity v times w, the absolute value of that. So the projection of v times w, u, this is what it looks like here. Geometric property of a triple scalar product. The volume v of a parallelepiped with vectors u, v, and w as adjacent edges is given by v equals the absolute value of u times quantity v times w. Let's try one. Volume by the triple scalar product. So find the volume of the parallelepiped having u equals 3i minus 5j plus k, and v equals 2j minus 2k, and w equals 3i plus j plus k as adjacent edges as shown here. So now the key word here is adjacent. You have a face here, then you have a face here, and then like that. So u, this is u, and then v, which is here, and then w. Where is w? W, this is v here and w here. That must be w there. The value of the triple scalar product is, here it is, u times quantity v times w equals this array here, 3, negative 5 and 1. This is u, and then v times, this is v here, 0, 0 to negative 2. And then w, which is 3, 1, 1, which is here. So having those three dimensions there, we end up with this sum here. This comes out to 3 times 4 plus 5 times 6 plus 1 times negative 6 equals 36. So the volume of the parallelepiped is u times v times w, u times the quantity v times w quantity absolute value will equal 36. And then you can check this on a CX calculator. It comes out to 36 down here by using your correct function here on the CX. Let's go into a guided practice. Use the triple scalar product to find the volume of the parallelepiped having adjacent edges u, v, and w. So here's u here, here's v here, and here's w here. So we have this face, and this face, and then this face. And then here are our componentized scalars, or rather our vectors. So having those vectors, we have u times the quantity v times w. Here is our matrix here. And that was 10.3 Part 2, Pre-Calculus Math today, classwork lesson. If you need course materials or you got questions that you need to need response to, email me at animatedpowerpointmathvideo@aol.com. Thank you very much.